click on it and actually open it up. I'll click around. Alright, so yesterday we started talking about reaction kinetics or reaction rates, how fast the reaction goes, and really that is looking at the amount of effective collisions within a period of time. We got partially through the list of the 5 factors that affect reaction rate. So the first factor was the nature of reactants. So what are the reactants? Are they ions in solution, or the gases, or what are they? That is the most important as far as how much it influences the rate. But we tend to focus on that the least because there's nothing we can do about that. Okay? If we're doing a reaction with ionic compounds, they're ionic compounds, that's all we can do. Okay? The other 4 we tend to focus on more because we have influence over those 4, okay? But they have less of an influence on the rate. So the second one was concentration. That was pretty logical. The more concentrated, typically the rate tends to increase. The third one is temperature. Temperature is a measure of what? Average or total? Average. Kinetic energy. So kinetic energy is the energy associated with motion. Okay? So in its simplest explanation, temperature is the measure of, on average, how fast the particles are moving. Okay? So it probably is logical that the faster the particles are moving, the more likely they are to collide. Does that make sense? If you're moving around faster, you're more likely to collide. And if you have more energy, you're moving around faster, you're more likely to have an effective collision, okay, that results in a reaction. So a collision with sufficient energy. So the basic rule is an increase in temperature increases rate for both endo and exo reactions. But typically, endo reactions are increased more. Okay? So increased temperature increases the rate for endo and exo, but it has a greater effect on endothermic. Okay? So do we think of energy as a product or a reactant for endothermic reactions? Reactant. Okay, so think about it in terms of adding more of a reactant. This one has a greater effect on that. We'll talk about that a little bit more when it comes to equilibrium. That has a larger effect on it with the next chapter. Okay, but I think you could have logicked through that one. Higher temperatures, faster motion, more collisions, the greater the rate. Okay. Questions about that? Pretty straightforward. Then number 4, we have surface area. We can say or particle size. So surface area and particle size refer to the same idea. So if I take a big chunk of something, and then I cut the big chunk into 4 cubes. So I went from 1 cube to 4 smaller cubes, which is a greater surface area. The big one or the 4 small ones? The 4 small ones have a greater surface area. So if you remember the whole deal with cells, the surface area versus volume, you probably remember that from last year with biology. So the greater or lesser the surface area, the faster the reaction, do you think? Yeah, probably the greater. Okay, so we can say greater surface area allows for a greater probability of collision. So a greater probability of collision means an increased rate. And so a really simple example of that is zinc reacts with hydrochloric acid to produce hydrogen gas in zinc chloride solution. So if I take 2 beakers full of hydrochloric acid and I add a chunk of zinc that weighs 5 grams, or I add 5 grams of zinc powder. If zinc is my limiting reactant or my excess, whichever it is, that is what determines how far the reaction goes. Okay? The particle size affects the rate. Does the rate have anything to do with if the reaction completes or not? No, stoichiometry takes over on that. Okay? So which one of these is going to react faster? The crushed up one, okay, the powder. It has a greater surface area. But assuming there's enough hydrochloric acid, will they both eventually react? Yes. So this has nothing to do with the outcome of the reaction. It has to do with the speed of the reaction. Same thing with dissolving. We talked about the giant crystal of salt versus the salt powder. In equal amounts, if it's soluble, they'll both dissolve, but they dissolve at different rates. Okay, so we're talking about how quickly it happens, not if it happens or not. Okay? Questions about that? Here's a nice little story about a dust explosion, if you read that at the bottom. I'll read that later. So, oops. Let me find some notes I hadn't written on. Sorry about that. So now, the fifth thing that has influence over the rate of reaction is a catalyst. So what do catalysts do from biology? What's the simple definition? So they increase rate by lowering EA. So what does EA stand for? Activation energy. So they really don't necessarily increase the rate directly. What catalysts do by definition is decrease activation energy. Kind of a byproduct of that is rate increases. Okay? So if you ever ask specifically what does a catalyst do, a catalyst lowers activation energy. Kind of a byproduct of that is it increases rate. So we tend to associate catalysts with an increase in rate. Okay? So the way they work is, from biology you probably learned, they provide an alternative pathway for the reaction. So we still have the same reactants, the same products, but the path is middle, or the path in the middle is different. So what do we call that middle piece between reactants and products? What was the new word for that? New phrase? The activated complex. Okay. So catalysts provide us with a different activated complex in the middle. Okay. So on this example, reactants, products, right here is my activated complex. Okay. So you can kind of use the analogy of the reactant climbing up the hill of the energy here. Okay. The reactant has to gain the energy, then go back down to get the products. Okay, or become the products. Think about it as actually climbing the hill. Okay, what is the slow part of the process? Going up or going back down? Going up. So what determines how fast the reaction goes? How far up the hill it is or how far down it is? How far up? How far you have to climb is the slow step. Okay, so if you have three things to do, and the first part takes 3 hours, the second part takes 5 minutes, the third part takes 5 minutes. Most of your time is determined by the longest step, right? Same thing here. Up the hill part is the longest step. So here, you go up the hill, you see another route, another option. So that could be our activated complex with a catalyst. Does it still have to climb the hill and gain energy? Yes. Is the activated complex still high energy and unstable? Yes. But is it as high energy as it would be if there were no catalyst? No. So did I change the overall energy of the reactants or the products? No. So did I change the reaction's delta H, the difference in reactant and product energy? No. So it's typed out right there. The delta H doesn't change. Okay. Does the activation energy change though? Yes. Okay. So we're changing the activation energy, not the energy of reactants, not the energy of products, not the delta H for the reaction. Okay. So typically, when we have a catalyst, we'll write it like this. We'll have something like A plus B goes to C, and you'll have something like PT over the arrow. What does PT stand for? What element is PT?
Oh, really?
It's platinum. Okay. Did you not learn that one on the list?
No.
Should have been. So that is the catalyst in this situation. So it's not written as a reactant, it's not written as a product, so we write it above the arrow because they are not reactants or products. So reactants are used up in the reaction, products are created in the reaction. So catalysts are neither used up nor created. So if I add A plus B plus platinum, what I'm going to get out is C and my platinum. It's going to be left over. It's involved in the reaction, but it's not consumed, it's not used up. Okay, I might have to add 1 mole of A plus 1 mole of B to make 1 mole of C, but it might be 0.001 moles of my catalyst, typically smaller amounts. Okay, so a couple of notes there. If you're in AP biology, you probably talk about different enzymes. You probably use the enzyme amylase for a lab last year in biology. Typically, catalysts are talked about in biology and biochemistry, different enzymes or catalysts. In non-biochemistry, the most common catalysts are transition metals, things like palladium and platinum and zinc. If you take higher level chemistry next year or in college, you'll talk about why they're good catalysts, but for now, just be aware that transition metals are typically catalysts. And then also, the situation arises from time to time where we want to slow down a reaction, okay, instead of increasing the rate. So we think of kinetics as being trying to make the reaction go faster and be better. That's not always the case. So if you think about a reaction that's extremely exothermic, what's it going to do? Absorb or release heat? Release. So if you're doing it in a large facility, a large plant of some sort, and you're doing a reaction in some kind of, let's say, steel container, and it releases so much energy that the temperature of the reaction surpasses the melting point of steel, what do you have?
A disaster.
A problem, right? So that could be a situation where you might want to slow things down, right? Make the reaction proceed more slowly so it releases the energy more slowly. A more common example of wanting to slow a reaction down happens in your body. So a lot of enzymes want to slow down reactions that aren't necessarily good for the cells. So the opposite of a catalyst we call an inhibitor. Okay, so catalysts speed up rate, inhibitors slow down the rate. So in this class we'll focus on kind of increasing the rate, but also just be aware inhibitors do exist. Okay, so let's really quickly review the 5 ways we can affect the rate of reaction. The first we have no control over, the nature of the reactants, what they are. The second through 5th we do have control over. Okay, concentration I can change, temperature I can change, surface area, particle size I can change, and whether or not there's a catalyst I can change. Okay, so make sure you can list those 5, and also just very briefly in simple terms explain how they work. So how do they change the rate of the reaction? Okay, the 2nd through 4th are pretty logical. The 5th and 1st you got to think about a little. Okay. Any questions about those? Good. So let's turn over to the next page. We'll come back to this at the bottom at the end of class or tomorrow. So everything we've done so far has been kind of qualitative in nature. We've just said the rate increases, the rate decreases. We haven't really said by how much. Okay. So what we'll look at now is a way to kind of quantify first a rate and then a change in rate. So it writes out reaction rates. We've used that phrase quite a bit, but what does that mean really? So how we define a reaction rate is the change in concentration, so I'll say delta concentration per unit of time. And so it's how much the concentration changes as time goes on. So if we're discussing the rate of reaction, we'll talk about how much or what concentration of A disappears as it reacts per second or whatever it might be. So what's our most common unit for concentration? Molarity. Are there others? Yeah. What's a unit for time? Second. What's the per tell me to do? Slash. So the common unit for a reaction rate is molar per second. Could also write that as moles divided by liters times seconds. Yeah, because molarity is just moles over liters. Okay. Now, could I have a bunch of other units like molar per hour, molar per day, or whatever? Yeah, fine. We'll tend to stick with molar per second. Okay. And there were some issues. I don't know why that printed as mailboxes, and we can skip over that. I don't know what's going on there.
What are they supposed to be?
A reaction arrow. So I don't know why my arrow became a mailbox. But
Two mailboxes, not bad.
It looks like
I don't know. So let's skip that and look down at rate laws. We can skip the mailboxes. So this is what we ultimately care about. We want to, for a reaction, be able to write its rate law. So rate law is an equation that relates reaction rate, and I'm going to write bracket reactants. So a new notation we have, when I write the name of something in brackets, that refers to concentration. So make a note up here, brackets NaCl equals concentration of NaCl. And that's very common in chemistry to just write something in brackets and refer to concentration. Okay. So brackets reactants means what? Concentration of reactants. Okay. So we need to come up with an equation or equations that allow us to convert between reaction rate and concentration of reactants. Okay. I left the word rate out. I was trying to talk and write at the same time. Sorry. Let's try that again. We want to relate reaction rate and the concentration of reactants. So basically, if I give you a reaction, whatever it might be, and I say, well, if the concentration of the reactants are this, how fast will it go? That's what we're ultimately trying to answer. So what a rate law ultimately looks like, just kind of the generic form of it, is we'll say rate equals K. What does K stand for? Constant. So K is a constant, and down here we can make a note, which that's constant, but it's unique for each situation. No. So Avogadro's number is a constant, but it's always the same, right? The rate constant K is specific to a special reaction and a certain temperature. Okay? So it's not a number we'll memorize, it's one we'll calculate. And we'll learn kind of why we use that later. But it's not something you'll memorize, you can't. It's different for every reaction and every temperature. So we'll say rate equals K times brackets reactant 1. So what does brackets reactant 1 mean? Concentration of the first reactant raised to the n power. So n is a whole number. Is 0 considered a whole number? With 0, 1, 2, 3, those are the options. So those integers, I guess. Whatever the name for 0, 1, 2, 3, 4 is, that's what those are. Okay. So n is a number that can be 0.
That can be.
Yes, it can be 0.
Okay. 0, 1, 2, 3, 4? Or can it be above?
Theoretically, it can go higher, but really it doesn't. Times bracket reactant 2 raised to the n. And the two n's do not have to be the same number. They can change. Then I'll just do dot, dot, dot. What does the dot, dot, dot after it tell me? I can keep going if I need to. Okay. If I have 2 reactants, it looks like this. If I have 1 reactant, it looks like that. If I have 3 reactants, there's another piece. Okay, so it's as long as you need it to be. Does that make sense? Yeah. Typically, 3 is the most you'll have. You can have more, though. Okay. So then one other phrase we'll use quite a bit is order. So we'll talk about what it means later, but for now, just know that order equals the value of n. So if I say, what is the order of the reaction, tell me what the value for n is. Okay, so first order, second order, third order. And an important note, n can only be determined experimentally. Okay, so this is also important. Put a star up here. it is impossible to figure this out by using the balanced equation. Okay? You cannot just look at a reaction and write the rate law. The only way to do this is from experimental data, to find it experimentally. Okay? So you cannot just look at a reaction and say, oh, the rate law is going to be this. Okay? You have to figure it out with an experiment. Okay. So, a little bit confusing. We'll do one or two and it should make a little more sense. Okay. So let's look down at this example. So for this example, I gave you a reaction 2 N2O5 produce 4 NO2 plus O2. That's my reaction. And what the box is, it's saying I went to lab and did this. Here's trial 1. Here's trial 2. So it's saying for trial 1, my concentration for N2O5 was 0.9 molar. When I use that concentration, my reaction rate was 5.4 times 10 to the negative 4 molar per second. Now, there's two different unit options in that second column. Are those two unit options different? No. Okay, capital M over S is the same thing as mole over L times S. Okay. So then I start over, do the experiment again, trial 2. This time my initial concentration is 0.45 molar. Then I record my rate. Is my rate the same? No. Does that make sense? Does concentration typically affect rate? Yes. So before we figure out what the numbers are going to be, let's write just the general rate law. Let's do as much as we can just by looking at it. So I can say rate equals K times concentration of N2O5 raised to the N. Okay. I can do that. We know that much. Do I need more reactants? I just have one. It's a decomposition reaction. So now I've got to figure out what the value for N is. Okay. So we have two trials. As I go from trial 1 to trial 2, I want to figure out what happened to my concentration. Okay. So let's just write it in. We can say concentration of N2O5. I can say 0.90 molar, 0.45 molar. So what's that when you divide it? 2. So trial 1 is twice as concentrated as trial 2, right? And I chose these numbers in the lab. Okay, so you get to choose the concentrations because you make that. Okay, so I chose to double or half. That's typically what you do. Okay, so going from trial 2 to trial 1, I doubled the concentration. Now let's look at the rate. So I can say 5.4 times 10 to the negative 4 divided by 2.7 times 10 to the negative 4. What does that equal? 2. So now, in words, I can go back and say, as concentration of N2O5 doubles, rate does what? Doubles as well. This is not a rule, okay? This is only for this specific example. You have to do it every time. It's not always when rate doubles, concentration is doubled. It changes from case to case. But do we see why I can say that here? Concentration doubled here, rate doubled here, okay? So now, how to calculate N? So I'll say 2, which comes from right there, raised to the N power equals 2. So I know this is, you can do it in your head, but go ahead and write this one out so when it's not this easy, you have an example to go back and look at. So show where those two 2's came from. So 2 raised to the N equals 2. So what does N equal? 1. So if my exponent's 1, can I leave it off? Yeah, but it's good to go ahead and write it in for this, that way you don't forget about it. So I can rewrite this as rate equals K times concentration of N2O5 to the first power. So now I can ask you, what is the order of the reaction? Is it zero order, first order, second order? First order. That's why it's good to write the 1 in. If you leave the 1 off, it's tempting to say 0. Okay. So we're on the road where we need to be, but given this, if I gave you a concentration, could you tell me the rate? No. What do I need to do that? K. So to solve for K, I need a rate and a concentration to go together. Do I have that? Yes. So I can choose trial 1 or trial 2, plug into this formula, and solve for K. Will I get the same number either way? Yeah, so go ahead and do that. So you can take trial 1 if you want to. So we can say that our rate is 5.4 times 10 to the negative 4 molar per second equals K times 0.90 molar to the first power. So to solve for K, divide both sides by 0.9. Okay. Then the capital M's are going to cancel. What is not going to cancel? Seconds. Is it only numerator or denominator? Denominator. So what are my units going to be?
Inverse seconds?
Inverse seconds. So 1 over seconds. Okay. So what number did you get for K? Six, maybe? 6.0. So put in scientific notation. So 6.0 times 10 to the negative 4th, 1 over seconds, or inverse seconds. So the units for K have many different options. If you go to higher level chemistry, the units very much matter. For this, we won't focus so much on what the units mean. In the past, we focused on units so much because they cancel and you can check your answer. This is not the case. They're not going to cancel and always be nice and pretty like you expect. You can have some weird units for K. So now let's rewrite it. I have rate equals 6.0 times 10 to the negative 4th seconds to the negative 1, it's inverse seconds, times the concentration of N2O5 to the first power. Now, if I give you a concentration of N2O5, something molar, could you tell me the rate at which it will decompose? Yes. Okay. You plug in capital M here, here, per second here, you get your rate in capital M over S. Okay. Now do I have a useful expression for calculating rate? Yeah. So I call this my rate law. Now, if trial 3, we're going to use a concentration of 0.57 molar, would I have to do trial 3, or could I just plug in the formula? Just plug in the formula, okay? And I'll point out, these numbers are perfect. And these examples are designed so the numbers come out perfect. In an actual lab situation, it would come out to like 2.01 or 1.98, and the trials wouldn't exactly match. Okay, but these examples for now they will. But in the lab they won't be quite so perfect. Okay, questions? Good. Let's look at another one. Turn over to the next page. So I'll give you a different reaction, but I ask you the same thing. Okay. One that's there. I ask you for the rate law. So 2HI yields H2 plus I2. So I can go ahead and write the general rate law. I can say rate is going to equal K times concentration of HI. We start off with decomposition first because they're easier, because they just have one reaction. Okay. So here I have 3 trials. So could I choose to compare any of those 3 trials? Yes, but the best way to do it is to find one where concentration doubles. Is there a situation where the two concentrations have doubled? Yes, I want to choose 1 and 2. Okay. So could I do 1 and 3 and get the right answer? It's a lot more complicated. Okay. We want to use one where it just doubles, makes our life easy. Okay. So concentration of HI, as it doubled, 0.030 molar to 0.015 molar. Okay. Express the bigger one on the top where it doubled. So that number in your head's pretty easily what? 2. You already told me it doubled. Then for the rates, we can say 4.4 times 10 to the negative third divided by 1.1 times 10 to the negative third. What does that equal? What's 4.4 divided by 1.1? 4. So now, in words, as HI, concentration, doubles, rate does what? Quadruples. So the whole concentration doubles, rate doubles doesn't always work. It can be different. So now let's figure out N. So down here, 2 to the N equals 4. What's my value for N? 2. So N equals 2. Okay, so now I know it's a second order reaction, but what do I need to solve for now? Okay, it doesn't matter if I choose trial 1, trial 2, or trial 3 to solve for K. Now let's just do trial 1. So I can say my rate is 1.1 times 10 to the negative third equals K times 0.015 molar squared. I left the units off, sorry. So it's molar per second equals K times 0.015 molar squared. Can't leave the 2 off there. So first, let's look at the units before we even divide. M squared is M squared. So capital M over S divided by M squared, one of the M's is going to cancel. But our units are going to be left with inverse M, inverse second. Okay. Do those units make a lot of sense? Per molar per second? No. So don't worry about the units for K being logical. As you go further in chemistry, you'll talk about it more. But for now, I'll just plug it in and solve for them. So what does the number equal for K? Somebody type it in for me. That doesn't sound right. 4.9 sounds more right. Let's say K equals 4.9. Inverse molar, inverse seconds. Don't forget to square that 0.15. So now let's rewrite it. Let's say rate equals 4.9 molar inverse second inverse concentration of HI squared. If you ever want to double check yourself, let's go to like trial 3. If I take trial 3 concentration and plug in here, what number should I get? Trial 3's rate. It's a good way to check yourself. Okay. And for the units, if you double molar, one of the molars is going to cancel, so you're left with molar per second, which is what we're trying to solve for. Okay. So now, if I give you any concentration for HI, if I say trial 4, the concentration is going to be 0.057, could you plug in and tell me what the rate's going to be? Yeah. Okay, so what do I call this? What's this thing on get circle called? The rate law. And this only applies to this reaction at the same temperature, okay? And the only way to get this is by doing the experiment and getting the data, okay? All this came from a lab, well, they're made up. But they would have come from a lab experiment, is where you get it. You cannot just look at the reaction and try to figure out what the constant is, okay? Questions about that? Okay, so that's as far as we got first period, so we can stop. But go back to the previous page and look at question A and question B. So answer those two, then we'll call it a day, okay? So question A and question B under the catalyst portion.